Hello, I am Seema and welcome to part 18 of the chapter Haloalkanes and Haloarenes. In the previous few parts, I was explaining the different kinds of nucleophilic substitution reactions of haloalkanes and haloarenes. And when I explained the two types of nucleophilic substitution reactions, that is SN1 and SN2, while explaining the mechanisms, I told you that in SN2 mechanism, there is an inversion of the configuration of the compound. Now, the inversion I explained with the help of an umbrella, where I showed that the bent of the umbrella changes, the direction of the bonds changes as SN2 mechanism takes place. Now, in order to understand the inversion of the configuration, the SN1 mechanism, on the other hand, undergoes a racemization. And in order to understand this, we must understand the stereochemical aspects of chemical reactions. So in this video, I'm going to tell you about the stereochemical aspects of nucleophilic substitution reaction. Now, what is stereochemistry? Stereochemistry, or in stereochemical, when we study about the stereochemistry, we study the directional aspects of the bonds and the different atoms which are forming the entire structure. And a change in the direction can lead to a change in the properties of the substance. The same compound may be having the same molecular formula, but simply because the molecule is arranged in the atoms are arranged in different directions, it may show isomeric forms, which show a difference in their properties. So let us understand this further. The first stereochemical aspect that we would be discussing in this video would be plane polarized light and optical activity. When I talk of plane polarized light, let us take an example with these pens. Let us imagine that light consists of different rays, and these different rays may be scattered in different directions. From a source of light, any source of light, the light that comes out would be scattered in different directions. If we pass this light through a prism, now here we have a nickel prism. When you pass light which is scattered, the rays of light which are scattered in different directions, when you pass it through a nickel prism, what happens is that it becomes plane polarized. It means when you say polarized, the direction, if you see the arrowheads, each ray is moving in a certain direction, and that is shown by an arrowhead. So all the arrowheads, they get polarized, or they get directed in one plane, or it is more or less as if they are present in one page. Do you see this? This is plane polarized light. When you pass light through a nickel prism, all the rays, they direct themselves in one particular direction in one plane. This light is now known as plane polarized light. The reason we want plane polarized light is that there are certain compounds which show an effect on the plane of polarized light. When you have plane polarized light, the certain compounds would affect the plane of polarized light. And that property is known as plane. You understand what plane polarized light is, and the activity that is shown by compounds is known as optical activity. So activity by a compound which affects the plane of polarized light. Light is optics or optical behavior, and it affects the optical behavior of light. Therefore, such compounds show optical activity. Let us understand this further. Certain compounds can rotate the plane of polarized light when it is passed through their solutions. If you take certain compounds, you pass light through a nickel prism and light becomes plane polarized. Certain compounds have if you pass this plane polarized light through a compound, the solution of a compound, the solution may rotate the plane of the polarized light. If this is a page like this, it will rotate it either to the right or it will rotate it to the left. This rotation is known as optical activity. So we say that this compound is optically active. It has a property that it can twist or rotate the plane of polarized light. So what is plane polarized light? When light aligns itself in one direction, the different rays. And what is optical activity? Optical activity is the property of a compound whose solution affects the plane of polarized light. If it affects it in the right direction, that is, if it rotates it to the right direction, we say it is dextrorotatory. If it rotates the plane of polarized light towards the left direction, we say it is levorotatory. L for left. So when it twists the light towards the left, we say it is levorotatory. When you twist it to the right, it is dextrorotatory. So such a solution would usually show one of the optical activities. It would either be dextrorotatory or it would be levorotatory. And usually when you have isomers, the different isomeric forms of the same compound may show opposite rotation. One of the isomeric forms may show dextrorotation, the other may show levorotation along the same angle. So if one of the isomers is dextrorotatory by 30 degrees, say, the other isomer of that compound would be levorotatory by 30 degrees too. So they would bend the angle of the optical of the polarized light by the same angle in opposite directions. Let us go into the details of this now. Certain compounds rotate the plane of polarized light when it is passed through their solutions. Such compounds are called optically active compounds. So the compounds which have the capability of twisting or rotating the plane of polarized light are called optically active compounds. The angle of rotation now, as I told you, that a compound may show, the two isomers of a compound may show rotation along the same angle in opposite directions. That angle of rotation, how is it measured? It is measured with the help of a polarimeter. It is helped with an instrument which is known as a polarimeter. So you use a polarimeter to measure the angle of rotation. And if the compound rotates the plane of polarized light to the right, that is, if the movement is clockwise, right? If this is a clock, if the rotation is taking place clockwise, it means the light is twisting towards the right. If the movement is anti-clockwise, it means it is twisting towards the left. So we say if it is moving to the right, we call it dextrorotatory. If it is moving to the left, we call it levorotatory. So if the compound rotates the plane to the right, then that is clockwise, then it is called dextrorotatory. And if it moves it towards the left, it is known as levorotatory. L is for left, so always remember levorotatory would be moving towards left. Also, let us imagine that this is a scale. Right? On a scale, if you see the integers, this is zero value. So this would be +1, this would be +2, this would be +3, this would be -1, -2, -3, and so on. So if the plane is twisting towards the right, or it is dextrorotatory, it is a positive value. So dextrorotatory compounds are also shown by positive notation. We say that it is positive. If it is moving towards the left, on a scale, negative values are towards the left. So if a compound is levorotatory, we also give it a sign of negative. So what are the different signs that we use? A dextrorotatory compound moves towards the right, its movement is clockwise, and it is represented by a positive sign. A levorotatory compound would be one which shifts the plane of polarized light towards left. Alright, since it is towards the left, it is moving to the negative direction, therefore it is negative. And since it is moving to the left, or it is anti-clockwise, moving to the left, we use the sign L. So for levorotatory form, we say it is the L form of the isomer. For a dextrorotatory form, we will say it is the D form of the isomer. Coming back to this now. So if the compound rotates the plane to the right, that is in the clockwise direction, it is called dextrorotatory, also represented by positive, which I just explained to you. On a scale in integers, if you move towards the right, you have a positive value. So dextrorotatory is positive and it is clockwise, and levorotatory on the other hand is negative. and it is anti-clockwise. These are also called the D form and the L form. D stands for dextro and L stands for levo. So the D is dextrorotatory form, L is levorotatory form. And such positive and negative isomers, or what is positive? Dextrorotatory, and negative is levorotatory isomers of a compound, are called optical isomers. So what kind of isomerism is this? Before I talk of the optical isomers, let us just be reminded of what isomers are. When you have the same compound, a compound that has the same molecular formula but different structural formula is known as, and those forms would be known as isomeric forms. And when these isomers are optically active, they show such optical activity that the two isomeric forms, one of them is levorotatory, one of them is dextrorotatory, such isomers are known as optical isomers. And the phenomenon is known as optical isomerism. So such dextrorotatory and levorotatory isomers of a compound are called optical isomers, and the phenomenon is known as optical isomerism. Now let us look at this diagrammatically once more. This was the plane polarized, this was light, normal light, where all the rays were going in all directions. We passed it through a nickel prism, and when we passed it through the nickel prism, we obtained plane polarized light. That is light having the rays in the same plane and all the heads pointed in the same direction. So we got plane polarized light. When we passed it through a dextrorotatory solution, what was supposed to happen? In a dextrorotatory solution, the plane of the polarized light would be shifted towards the right. And therefore a clockwise rotation took place, and this isomer was dextrorotatory. So do you see here all arrowheads are, the entire plane is twisted to the right according to a certain angle or by a certain angle. And if we pass the same plane polarized light through the other isomer, which was levorotatory, the negative solution, that is the levorotatory isomer, then the plane of polarized light would be twisted by the same angle towards the left. And that is what we see here. The light is twisted anti-clockwise. So the plane of polarized light is twisted by the same angle in the opposite direction, which is anti-clockwise. Rotation takes place by the same angle, and therefore in these two beakers you have isomers of the same compound, which are optical isomers. So this was the first optical or stereochemical aspect that I would like to explain. After this, why does this happen? Why do these compounds behave differently? Why do they show this optical activity? In the next video, we'll talk about chirality, and we'll talk of chiral compounds, we'll talk of asymmetry. What are the properties that make compounds optically active? And then we'll come to the SN1 and SN2 mechanisms to understand why they are different. So with this, I'll wind up this video. If you found it helpful, give it a thumbs up, subscribe to my channel, recommend it to your friends, and please keep returning for more videos in chemistry. Thank you for watching, and bye-bye for now.